Welcome to RISE Learning Machines seminars. RISE is Sweden's research institute with nearly 3,000 researchers working all over Sweden on research areas spanning from bioeconomy to material science, transport and digital systems. Our weekly Learning Machines seminars are organized as part of our Center for Applied AI Research. Today's meeting will be recorded, and if anyone wants to be removed from this recording, please let us know. I should also add that we have a really nice collection of recorded seminars on our YouTube channel. Check out the webpage and visit these. Today, it's my absolute pleasure to introduce Martin Hellkvist, who is a PhD student at Uppsala University. He got his master degree in electrical engineering from Uppsala University. His interests are within signal processing and machine learning with overparametrized models, and also some theoretical work around these. He's published works on distributed learning and double descent. Today's talk is about fake features that can improve estimation performance. And with this said, I will hand over the word to you, Martin.
Okay, thank you very much for the nice introduction. Let me just start sharing my screen here. Yeah, it's a pleasure to be here and get the chance to present my work in this type of format. As Olof said, the main topic of today will be our study of fake features and its connection to the double descent phenomenon and overparametrized models. And this study has been carried out during my PhD studies, of which I have 1 more year left at the Signals and Systems groups at Uppsala University, which is part of the electrical engineering department. So can we just confirm you see my slides? Yeah, okay, great. Yes. So the study I will present today is quite analytical and focuses on estimation fundamentals. And I hope that you will find it interesting and enjoy the talk as much as the title is catchy. So to set the scene, I would like to give some motivation to our problem by introducing you to the double descent phenomenon and overparametrized models. And then I will present the problem formulation, which is set up to study the double descent phenomenon using this concept of fake features. I will then give our analytical findings together with like some visual representations and simulation results, and then continue with concluding the talk. Okay, so now I will give a brief introduction to the double descent phenomenon and talk about how overparametrized models have come to defy some of the wisdom from classical estimation theory and learning theory. Finally, we will glance over some literature and see why it can be a good idea to study linear models. So in the supervised machine learning problem, we are giving a set of training data with the variables y as the output data or labels, and the variables a here as the inputs. And we are to learn a function f, which can approximate y well when a new input a comes. So we choose some model or architecture, for example, some type of regression, maybe neural networks or a random forest, to express this function or mapping f, which we then train using different learning schemes and optimization techniques. The training or learning of the function f is done over a set of training data, here we denote it with dn, while we use another set of data to evaluate the performance of this or quality of this function f. We refer to this new unseen data as either new data or test data. An important challenge here in this type of learning problem lies in that the error that we make on the training data while we are learning f is not exactly the same as the error that we make on the test data. So the error when new data points come, when we deploy our model. And traditionally, we have been taught that there's a trade-off between doing well on the training data versus doing well on the test data. And this notion is encapsulated in the classical wisdom of the bias variance trade-off, which is a guideline we use when it comes to determining appropriate model complexities or model size. So this plot to the left is a typical plot depicting the bias variance trade-off where you have the model complexity on the x-axis and the test error on the y-axis as the red curve here. And this test error is decomposed into a bias component and a variance component. And what this trade-off tells us is that models with low complexity, so to the left on the x-axis, will perform badly and have a high test error because they can't express the nuances of the input-output relationship that is actually in the data. And therefore, their estimates are bad both on the training and on the test data. Models with high complexity, on the other hand, so on the right-hand side of this curve, will instead have too much expressive capacity and overfit to the training data. And these mappings or functions will vary a lot if we just change the training data a little bit. And they are likely to do really bad on test data, even if the test data is close to the training data in distribution. And this trade-off in complexity leads us to this typical U-shaped curve, which illustrates that there should be a sweet spot in terms of complexity to get the best test error possible. And another way to illustrate this is in the figure to the right, where I have performed a couple of polynomial regression examples on these blue data points, which are the training data here. The red curve comes from a third-degree polynomial regression. And with the polynomial regression, I mean that I take the x data on the x-axis and transform it into x squared up to whatever degree I want to use for the polynomial regression. So while this red curve doesn't really pass through any of these blue data points, it is quite close to all of them. And as long as the test data that comes later on will follow the same type of distribution of these blue data points, this function should perform quite well on that test data. The yellow curve, on the other hand, which has a high polynomial degree, completely interpolates the training data. So it passes through all of these training points, and it obtains a zero training error. But as you can imagine, if test data comes even close to these, even if the test data comes close to these blue data points, the function is way off because the peaks and values of this function go far beyond like the dynamic range here of the training and test data. So this high degree polynomial will not perform so well on test data. So we say that it has overfit to the training data. Of course, it is not always true that the test data will come close to the training data, but for the sake of this example, we assume that they would. So while this classical U-shaped curve holds true for model complexities up until the point of interpolation, so where the function will go through all the training points, recent results and literature have found that it doesn't tell the full story, and that there's much more to explore to the right of this peak in variance if we increase the complexity even further. So in fact, results from deep learning research have shown that models with very high complexity can achieve a much better test error than what they could in the regime of this U-shaped curve. This type of curve is called the double descent curve. As you see, it first descends along the U-shaped curve, goes up to a peak, and then as we increase the complexity even more, it experiences a second descent into the overparametrized regime. And here's another example of a neural network exhibiting double descent. And the training error here is plotted in blue, and the training error is plotted in orange, sorry, and the test error in blue. So on the x-axis, you see the number of parameters in the network, which corresponds then to the model complexity. And as you see, the training error more or less decreases steadily as we increase the size of the network, going close to zero. The test error, on the other hand, first decreases along this classical curve, and then goes up, and then goes down as we go past this point of interpolation. So we will refer to the regime on the left-hand side of this threshold as the underparametrized regime, because we have the number of tunable parameters P is generally smaller than the number of training samples N. We refer to the regime on the right-hand side of the peak as the overparametrized regime, where we have more parameters than we have training samples. Recently, there's been a large amount of interest in the double descent phenomenon, which has led to a large amount of literature reporting how a wide range of models exhibit this double descent behavior. These results illustrate the potential benefits of using these massively over-parameterized models, which have much more parameters than you have training data. And this defies some of this classical wisdom from estimation and learning theory. And there's currently a large amount of effort being put into understanding when these over-parameterized works and why they work in order to effectively utilize their full potential. Here you see some recent publications which have reported and studied this phenomenon. And I don't want to go into too much detail, but mainly I want to highlight as well how many of these recent studies make use of studying linear models, which has been very impactful when it comes to pushing the understanding forward. We turn to these linear models because performing rigorous mathematical studies on nonlinear models can be quite challenging. And linear models instead offer less intricate paths to tractable expressions and explanations. And then we can hopefully use this knowledge as stepping stones into understanding more about complex and nonlinear models. So now we have covered some of the background and motivation. We looked at some literature, and I want to move on to presenting our setup and the findings that we found. So as you shall see, we focus on data which comes from a linear system and estimation with a model that doesn't match this underlying system generating the data. And there's a mismatch, and the main mismatch that we consider is represented by this concept of fake features. But before we go into more detail on that, we will consider a small real-world example. So first, a bit of disclaimer. I want to start off by saying that I'm not a biologist, and that this example is not a part of my research per se, but I just want to use it as an illustrative example to set an idea of why we can study fake features to gain some intuition about this type of curves. So in this data set, which is called the liver toxicity data set, we are given a set of toxin level measurements from blood tests, which corresponds to a certain type of liver damage. This toxin level we consider as our output variable. And along with each blood test are measurements of the gene expressions of over 3,000 different genes in the DNA sequence of the subject. And with this data at hand, a natural question is, which genes should I observe to predict the toxin level? Or rather, how many genes should I use to predict the toxin level? And this maybe can be translated into a bigger question of, can I predict this type of liver damage using a DNA sequence? So the estimation procedure we consider here is just to be seen as an initial, perhaps simplified attempt at answering this maybe difficult question. But we formulate a linear regression problem and observe how the test error changes as we increase the number of genes that we observe in the regression. So here I have plotted the MSE, so in terms of the output, the prediction error, versus the number of genes that I have in my regression problem. And the 4 different curves are for 4 different regularization levels. So a larger sigma hat here means that I regularize my regression problem more. So as you see for the small noise assumption, we get this type of double descent phenomenon as we increase the number of parameters, number of genes we observe. And it even looks like the best overall number of genes to observe is far to the right in the curve. So it looks like we should observe as many genes as possible. However, studies from biochemistry on this particular data set report that if chosen carefully, between 50 and 200 genes should be enough to predict the toxin level to an acceptable degree. So what is really going on here? Why is our example suggesting that we take as many as 1,000 or even more genes? So this is where our study of fake features come in and perhaps can explain why do these curves suggest that we should choose this many genes. Because if we choose so many genes, it seems like a lot of them should be excessive in terms of predicting the toxin level. We should be able to do it with only 50 or 200 genes. And these excessive genes can be interpreted as fake features, which we consider here. And I will explain later on why adding them can improve the estimate that we obtain. So now we will look at the problem formulations and later get on into our findings and come back and revisit this experiment to see what's actually going on. So we consider an output vector y generated by a linear underlying system, here, equation 1, where the feature matrices AS and AC are multiplied with the system parameters or unknowns, XS and XC. And then in this setting that we consider, the feature matrix AC goes missing and is not available for us to use during the estimation process. So we are missing some data, we're missing features. So naturally, we then asked ourselves when looking at this problem, what happens if this missing data is replaced by other data? What if that data is fake, if it doesn't have anything to do with the observations Y? So we introduced this misspecified model where the missing features AC has been replaced by the fake features in AF. And while performing estimation, we kind of believe that this AF matrix can be useful, so we include it in our estimation procedure. But in reality, it doesn't carry any information of the outputs or any of the other features in the data set. So we refer to these AF as fake features. And I just want to note also that we're not considering a setting here where we want to get rid of the fake features or detect them in any way. Instead, the main question we ask is, how is the estimation performance affected by the presence of these fake features? So what happens if we just blindly go and do this? Because we think that's an interesting question that can be interpreted in many different ways. So at this point, I want to pause a little bit and ask some interesting first order questions here to set the scene a bit more. So the main question that we ask going into this problem is, how is the estimation performance affected by the presence of fake features? Are the fake features in AF purely malicious? Should we avoid them at all costs? Or is there some more nuance to it? And furthermore, we also consider, is there any difference in terms of fake features if we estimate XS, so the part of the underlying system that we observe, versus only considering the output MSE, so the prediction error? So with these questions asked, we will look a little bit deeper into the setting and proceed to the findings. So as I said, we have our underlying system, which we consider to be a statistical system model, where the unknowns and noise are modeled as Gaussian random variables. And with the mean squared error in terms of these XS and XC components, the MMSE estimator is given by the cross covariance between X and Y multiplied with the pseudo inverse of the covariance for Y, which if opened up with this linear system model, turns out to be this expression. And using this linear optimal estimator, WO, we get the estimate for X, which is X hat, as W times Y. So this estimator is the best we can do in terms of XS and XC if we have the full knowledge of the model and this respective covariance matrix. So because to compute this WO, you see that we need to know what is the covariance in X, what are the features AS and AC, KX comes back in here, and we also need to know the covariance for the noise vector perfectly to get this estimate. But as I said, in our setting, we don't have this full knowledge of the system. We have to instead rely on this misspecified or mismatched model. And in this misspecified model, as I said, AC is replaced by the fake features AF, and we denote some kind of virtual unknown as XF. We have this noise vector V bar, and now we denote the covariance matrices as well as we believe them to be as K hat for XS and K hat for XF, as well as K hat for V. So these covariants are neither correct in terms of the underlying system as well, right? So we have to estimate them or assume some belief on them as well. But then we take the formula of this MMSE estimator, because that's what we want to do. We want to perform MMSE MMSE estimation here. So we take the formula because we believe that we are doing the right thing. We think that we have the right covariance and features. So doing this formula, we plug in the AF, the fake features down here. We have the assumed covariance matrix K hat for X, and the assumed covariance matrix for the noise as well, K hat for B. And we get an estimate of what we call X bar, which is this W bar times the output vector Y. So using this misspecified estimator, we are interested in the MSE of the respective sets of system unknowns, which are XS, XC, and XF. So we take each estimate, X hat for S, X hat C, X hat F, and we formulate these MSE components. And as you see, we with our misspecified estimator, we leave out XC because we don't have any information of it. So X hat C will just be set to 0 here. So the error will be just the power in XC. And in XF, there's actually no like true underlying value for it. So it ends up just being the power of the estimate that we put into it under a misspecified model. Furthermore, we also model the feature matrices as standard Gaussian matrices. And so you see that they are also included in this expectation measure that we take here. So it's not only the expectation over the distribution of the system parameters X and the data Y, it's also the features A. Then we also consider the performance criterion of the test error, so the output MSE, in terms of this misspecified estimate that we obtained using our misspecified model and the misspecified estimator. So a new data point comes according to the true underlying system, because that is still what is generating the data. So we get Y as AS XS plus AC XC plus some measurement noise. And then when we make a prediction, we use our misspecified estimate, right? So then we get a Y hat, prediction of Y, as AS XS hat, AF XF hat. And then we formulate the test error epsilon Y here as the output MSE. So you see Y minus Y hat squared. We take the expectation of over all the random components. We open up the expression and simplify, and we see that we end up with these error components from the previous slide, this epsilon S, epsilon C, and epsilon F. So these components that we formulated actually make up a decomposition of the output MSE. So as we move on to our findings now, we will see that this type of decomposition is actually very interesting and powerful to study, as if we were only looking at the output MSE, we could be hiding away some of the dynamics that these components can exhibit by themselves. So by studying them by one, we maybe can gain some additional insights, which we wouldn't see if we only looked at the output MSE. So here I present our main results, which are closed form expressions of the expected MSE of each respective set of the unknowns, XS, XC, and XF. So you see these expressions here. They are split into two sets of equations because we have one type of dynamic in the underparametrized regime where n is larger than p bar, and the other set here is for the overparametrized regime. So I don't want to go into too much detail on this slide because it's a lot of cluttery equations. And instead, I will go on to show some plots of these expressions, which illustrate the characteristics more visually. But although these expressions are not exactly straightforward to get a sense of, we can just note that we have successfully expressed the three different components as functions of the problem dimensions and the underlying covariance matrices. So you see that each of these components is actually just a function of the underlying or the problem dimensions, like PS, N, and P bar is the sum of PS and PF. So the number of underlying features plus the number of fake features. and n was the number of training samples. You also can note that the structure of the covariance matrices KXC and KXS have washed out, so we only get the trace of them actually still here. And this kind of simple form actually means that we can evaluate these error functions in a straightforward manner by just inserting the respective problem dimensions and signal powers. We can evaluate how the test error curve will look. So the main contribution here is that these expressions quantify how fake features affect the estimation performance, as we shall see in the following slides now. So here we have, in these plots I will show you, we fix the number of training samples and observed features PS, and we only vary the number of fake features. So on the plots, we will have PF, the number of fake features on the x-axis. So in this setting, we have fixed the number of training samples n to 200. We have 90 included features PS and 10 features that are missing PC. So you see the number of fake features on the x-axis. And then regarding the normalization, you see that the level of 10 to the power 0, so 1, corresponds to the error that we would make if we only put zeros into our estimates of x. So if ever the MSE is below this level, then we are actually learning something about the estimation. And if instead the MSE is above this normalization level, then we're actually only making more mistakes than we need to. So the baseline here corresponds to the power of the unknowns, trace of kx, plus the noise power. So the first thing to notice in this plot is that our expressions indeed do match the simulations. The markers denote evaluations of the expressions, and the lines in the plot come from simulation. And we also observe for this epsilon y, we observe a double descent type of behavior as we go into this overparametrized regime. Right, I should mention, given these problem dimensions n200 and ps90, this interpolation threshold would be at pf equals 110. So then pf plus ps is equal to n, which is 200. So that is where we interpolate the training data. So you see this peak comes just there with pf equals 110. So yeah, as I said, as we increase the pf to push the problem into being overparametrized, we see this second descent in the test error. So you see the test error, it actually never goes below this baseline error as I talked about. So it means that in this setup, we won't be able to add fake features to predict the output to any significant extent. So we're only doing worse than we would have to if we just put zeros everywhere. But on the other hand, you see another dynamic for the error in the underlying unknowns, XS. So this epsilon S component, which is the orange curve. You see it has a global minimum actually in the overparametrized regime, which is below its own baseline, which is around 0.45. It's only the trace of KXS. So this means that we are actually learning something significant about the underlying system here, even though we're not able to predict the output. So you see here the interesting result, which comes from decomposing the error Y into components XS, XE, and XF. You can also look at the error in XC, as it was always going to be only the power of XC component. It is constant here. And you see that the epsilon F curve has a dynamic which just, when you add it together with epsilon S and epsilon C, you will get up to this epsilon Y curve. So these three together then makes up the epsilon Y, the error output MSE. And this type of dynamic that we can learn about the underlying system, even though the prediction error is uninformative, or the prediction that we can make in Y is bad, can actually be very interesting if, for example, these unknowns XS that we are observing maybe represent some kind of physical or chemical process. So they have some underlying physical meaning that we're interested in evaluating, and maybe not only predicting the output variable here. So for example, in the genetics example we talked about earlier, we're interested in can we estimate the level of this excess component here, which then would correspond to like how impactful the one specific gene is in terms of the output variable. So, okay, so now we have seen some of these underlying characteristics of the learning procedure, which we wouldn't have observed by only focusing on the output MSE, and that this decomposition we've made give us actually some additional insight. But now in the next slide, we will focus more attention on just this epsilon s component. So in this figure, we plot the error of epsilon s, which is in respect to these included underlying features, excess. And as we discussed, this error curve corresponds to what we're learning about the underlying system dynamic. And it is in fact a component of the output MSE. So on the y-axis, we have, again, the normalized error, which is now a trace of kxs. So the baseline now is then on this 10 to the power 0. And on the x-axis, we have the number of fake features again. We have plotted the setting here for 4 different noise levels, so sigma v. And the number of included underlying features here is PS is 100. We don't have any missing features, and the number of samples is 200. So here the interpolation threshold would be at PF equals 100, right? So 100 plus 100 is 200, which equals the number of samples. So yeah, we observed that all these error curves increase as we approach the threshold, and then experience this second descent as we enter the overparametrized regime, being on the right-hand side of the peak. And the most interesting curve here is again the orange curve, which is for this medium noisy case where the noise has scaling 10. And the descent into the overparametrized regime reaches this global minimum, which is indeed a lower error than for the case without fake features. So you can note here that adding fake features, adding a lot of fake features, even into the overparametrized regime, the error of the orange curve will actually be lower than it was without any fake features, which is far to the left. So adding these like irrelevant fake data can actually make us learn more about the underlying system here. And we interpret this gain in information like that the fake features bring some type of implicit regularization to the problem that is beneficial in this medium to high noisy setting. And we note that we also need enough fake features to make the problem overparametrized to gain something from them, as the error always increases monotonically with PF in the underparametrized regime. So you see for every of these curves, the error just increases with PF here to the left.
Question, Martin.
Yeah, sure.
Is it the global minimum in this plot in the underparametrized regime for the red line?
Yeah, right. Good point. For the red line, there's no use actually of having fake features at all, because you see the best number of fake features is always 0 on this red curve. You generally just go up, up, up when you add them. So to have any gain, you have to have, like the noise level has to be high enough so that this regularization that the fake features bring to the table actually have some noise to regularize away, right?
Okay, but I mean, if you go to the orange line, it never goes below the red line in the underparametrized regime.
Right. Yeah. So those are for different noise settings, right? So it's like 4 different data sets on this, 4 different examples on this plot. So the red line is when noise level was 1, and the orange line says noise level is 10. And that is not something we can control. It's just a property of the data set. How noisy is my data?
Okay, so it's noise. It's noise also for the real features. It's not just the fake features.
Yeah, the noise is just the additive noise to the output vector.
Okay, good.
Additive Gaussian noise.
Okay,
good point.
Thank you.
Yeah. So yeah, we see that if the noise is high enough, then the fake features can regularize some of that effect away. Yeah, so to kind of summarize this plot, we see that even though the fake features have nothing to do with the data, since they are independent from the outputs Y and the features AS and AC, their presence can actually improve the quality of the estimate of excess. And the error curves as well are not monotonic functions of the number of fake features. So generally finding or knowing the overall optimal number of fake features is non-trivial. So looking at this curve, you can kind of think, can I figure out how to get to this kind of minimum in the overparametrized regime? Or in another way, I don't know which number I should choose, because in some cases, PF equals 0 is not the best choice, like for the orange curve. So now we will move to another type of result. Here we have another type of plot, and we're trying to compare this implicit regularization provided by the fake features to an explicit regularizer provided here by the noise level assumption. So that is you see that this sigma hat represents our noise level assumption, like how noisy do we think that the data is. So if I put that to non-zero, I regularize my problem even more. And you see here in the estimate that it comes in similarly as the ridge regularizer would do in a ridge regression problem. So on this plot, we plot the MSE again, epsilon s here, versus the noise level assumption parameter sigma hat. So if I go further to the right, I regularize my problem more with this sigma hat number. And each curve you see represents a different number of fake features. So I consider some different experiments here. So the blue curve is without any fake features, just having the AS and no AC or AF. But then as I go up through these curves, I increase the number of fake features even more. So the main interesting thing here is that we observe some kind of trade-off between the regularizing effect that these two entities provide, the fake features and the regularizing sigma hat. So you see on this blue curve, without fake features, that the best sigma hat I can choose, which to minimize the MSE, is sigma hat equals 10. This is the minimum on this curve. But as you consider, if I increase the number of fake features to 500 and look at the red curve, the minimum MSE in terms of sigma hat is much further to the left and perhaps almost 0 here. So you see that if I have more fake features, they are regularizing the problem for me already, and I don't have to put this explicit regularizer in. So while both the fake features and noise level assumption provide regularization to the problem, so there are similarities in how they work and what they do, there's also an interesting distinction to make between them. So this is summarized on this slide. And you see the form of the estimator in the overparametrized regime here, where P bar is larger than N. I can write the estimator in this form. And you see that if PF is much larger than N, so I have a lot of fake features in relation to the amount of data I have, this AF times AF transpose would be some kind of scaled identity matrix, scaling with the number of fake features that I have. And you see that this, if I insert this into the expression above, I'm actually adding the identity matrix 2 times here, both with the PF and sigma hat. So they both come into the estimator in the same manner, right? Although I have AF up here outside my inverse as well, which is another part of the story, I think. So that's like their similarity, but then you also see how they are dissimilar in terms of the interpolation, actually. So again, in the overparametrized regime, I write my prediction for the training data. So Y is my training data vector, and this Y hat is my estimate that I make on the training data after I have performed the estimation. So I plug in my X hat, which is equal to W times Y, and it will have this form. So you see that if I set sigma hat to 0, we will just have A bar transpose, A bar transpose inverse, and I will actually get interpolation here. So Y hat will be equal to Y. But if I increase sigma hat, I will disrupt this relation and no longer interpolate. Maybe you have seen that when you play with ridge regression, if you increase the ridge parameter, you will increase the training error, but improve the test error. I think it's an interesting dynamic here to see how these two type of regularizers work. And yeah, A bar here, as I noted in the top, is the composition of AS and AF together. So AF is in this equation 10 here, right? So even though we have fake features, provide some implicit regularization, we're still interpolating the training data. So let's now revisit this genetics problem and see what was happening there. And as I said earlier, about like 50 to 200 genes should be enough to predict the output. And as our experiment suggested, we should choose much more than that and have a large excess of gene in comparison to these 50 or 200 genes. And now that we have seen that the fake features can give some implicit regularization to the problem, we can actually interpret this decrease into the overparametrized regime with a lot of these excess genes as they are lowering the MSE just by giving this implicit regularization, as we saw from the fake features. So we are interpreting these excess parameters or excess features as fake features in our case. So this brings me to the main conclusion of the study, which is that even though they bear no information of the system or the data, fake features can actually improve the estimation performance. And we interpret this performance improvement as a kind of implicit regularization to the problem in the overparametrized setting. And in the medium to high noise settings, a large number of fake features can actually be the overall best solution to the problem if you cannot get rid of them. Or yeah, adding a lot of them will give you better than having no fake features actually. And we have also observed that the regularizing effect of the fake features is at a trade-off with the explicit regularization provided by the noise level assumption. And to derive this exact trade-off analytically remains a challenge, as well as deriving the closed form expressions for the MSE and test error for more complex and nonlinear models, which is something we look forward to explore moving forward. I think before we open the floor, I want to also give some special mentions to some of the results that didn't make it into the main part of the presentation. The first one being that we actually proved that there is a potentially global minimum of the error in the overparametrized regime. So as you saw on the curve, we can actually prove that it will always exist. And we also investigate the analytical expressions with the non-zero sigma hat assumption, which takes on this form. And you see that we can give it up to the expectation over the eigenvalues of the regressor matrices or the feature matrices. And another result that I find interesting is that we give for the massively underparametrized setting where we have a lot of samples in comparison to the model size. And then we can give the optimal noise level assumption as a function of the number of included features and the respective signal powers here, as well as the noise power, in order to minimize the error in the underlying components. So the work I presented here today, I did together with my two PhD supervisors here at Uppsala University, Aisha Özçelikale and Anders Alén. And here you see a list of our publications on this topic, where you also can find more information. The main paper is marked here in blue, and the paper above it is like a preliminary work to that paper. And in this third paper, we have studied a distributed learning setting, which actually has strong connections to this mismatched model perspective that we consider here, although this problem today was in a centralized learning setting. And with that, I think we can open the floor.
Thank you, Martin. Do we have questions from the audience?
I have a question.
Yeah.
First of all, thanks for the interesting presentation. But I was wondering if you can share a little bit on your thoughts on how these fake features would influence the nonlinear models.
Yeah, it's a very interesting question. And I think that like when you put perhaps like neural networks, for example, where you just blow up the model size with how it works with these connected neurons and nonlinear activation functions. You see that we have seen, for example, that like you can improve and give some implicit regularization by this like dropout ideas. You throw out some of the neurons, and maybe those were fake in a sense. They didn't provide enough information in terms of the label or the problem at hand. So I think like whenever you have this large amount of neurons or tunable parameters in your model, some of them will like be not so related to the output. And there's like, so these fake features can maybe also be seen as like an edge case or a extreme case of the weak features concept, where the features are like not entirely fake, but very, very weak in terms of expressibility of the output. So I think there is some connection there where you just blow up your model and maybe you end up with something that is unrelated to the output or very weakly related. Good question.
I also have a question.
Mm-hmm.
Yeah, thanks for the presentation, Martin. I was curious while like listening to your presentation, I was sort of all the time thinking about that there is this kind of result from the mid-90s, I think it's by Chris Bishop, where he shows that adding noise to the input data acts as a Tikhonov regularization. And I was just curious, do you see any parallels between sort of adding noise to features as opposed to essentially creating fake features?
Right. So there is probably a connection. It's a great point you make. Like when I add these fake features into my belief of the model, maybe that can be seen as some kind of noise. But then as we saw here, it also has to do with the like dimensionality as well. But there's probably some interesting connection there.
Yeah, I was just curious primarily.
Yeah,
I don't have any expertise in this, but that was sort of ringing the bell all the time.
Yeah.
While you
Yeah.
were presenting it.
Great question.
So Leif Jonsson here. I have a question also. I don't fully understand this, but are you saying these fake features you could you just add random values, random noise there, or do they actually have to? I mean, in the gene example, I guess at least that's gene data, right?
Yeah.
But could you just replace that with random noise? Would it be the same or?
That's a very interesting idea. Maybe I should have tried to do that, just like pushing these actual Gaussian data. But yeah, in this setting that we consider, they are just Gaussian data. They are unrelated to the training data, right? And it's an interesting question to see, like, what if my underlying system has another true distribution, which is different than from the distribution of the fake features that I add? How does that affect the dynamics? It's a very interesting question, like going forward, I think. Because there are a lot of like results as well on like distribution mismatch as well. Like what if I assume the wrong type of distribution on my data? That should have some interplay with this concept, I think.
Okay, thank you very much.
One more question from my side. Martin, you mentioned that you're probably gonna go for, or ideally you would like to also analyze a nonlinear case, because that's obviously what we use in all the modern neural networks. Like, do you see that's going to, you know, require like some kind of major difference in the analysis methodology? Because we all like linear systems,
Yeah.
of course, because they're relatively easy to analyze.
Yeah. So like, I think the first step I would take would be like to consider like a 2-layer shallow network where I just transform my data with like some kind of simpler model, or like not simple, but maybe like a random feature model or something like that, and try to see how the distribution of like maybe the spectral decomposition of the feature matrices are affected by that, and there should be some kind of opening, I think, to go into nonlinear models.
That makes sense. Thanks.
So I have a question also about, did I interpret it correctly that this method of adding features is mostly relevant in problems where you have low number of data points as compared to the number of, known features, or is it also relevant if you have a large amount of data points compared to the number of features?
Right. Yeah, so I think that if I go back to one of the plots on that, like if I consider the left-hand side of the plot here, and if I would increase the number of samples, the overall levels on the left-hand side would just keep on going down, because you would then be averaging out the measurements, noise, and those kind of you get that kind of dynamics, because like having more data is king as long as you are under-parameterized. But then if you have very few data, as you said, in relation to these true unknowns, you would start up very close to this peak, right? And you would be high on these curves. So then there is no real method or way to go back to the left, because you cannot make PF negative here. So you would just have to keep increasing and cross your fingers and go down this slide into the overparametrized regime and hope you end up under the curve. But I'm not suggesting you should add these fake features. They're just like, it's interesting to see how they compare to like explicit regularization, and they will just be there a lot of the times if you're not fully aware of how your data set looks. Like maybe you don't know how to detect them or get rid of them, really. But yeah, it's interesting to see that I can just add fake data and hopefully go down into this along this overparametrized curve.
Just as I'm thinking now, and maybe this is completely off the charts crazy, but one way of thinking of it, would it make sense to think about it as a way of almost a learned regularizer, in the sense that you have some random noise coming in, and as you're doing backprop, the kind of, you would assume that the weights assigned to those fake features eventually will go towards zero, but initially they will tend to have very high coefficients.
Yeah.
So if you think in the linear case, you're kind of conditionally both adding and multiplying noise to the real features in some sense that will eventually go towards zero. So, I mean, does it make sense to think about it in that way, as almost as a learned regularizer?
Yeah, I think there's definitely some connection there. It is difficult to see here, since this is like a batch problem, just a one-time, one-step solution. And when you talk about backpropagation, you're doing it in iterations.
Yeah, that's true. That's a good point.
It would be really interesting to see how these fake features work in like an online setting or iterative way. But what happens when I increase PF even more to like this 10 to the power 4, you see all these curves converge to like the baseline error. And that is because then I'm just putting too much regularization into my problem, and everything goes to zero, including what I'm learning about the included unknowns. So that is similar to just putting a too high ridge parameter, or forgetting too much in an online setting.
Right. And so if you would put it in that online setting or iterative setting, I mean, it would also be interesting to see kind of the lack of better words, but the attention vector in sense of kind of the magnitude of the coefficients for the fake features as they kind of change between layers and also over time as you're training more and more batches.
Yeah, for sure. I think what you would end up, if I would guess a little bit, I think you would end up seeing like this, if you were able to sort them, so you have all the fake features related components over here, they would just be like a block of white noise kind of, while maybe the components you would be learning, they would behave in some more structured manner. So maybe there's something to like detect what is fake and what is real in that online setting. That's a really interesting question.
Thank you.
Thanks.
Do we have some final question from Martin? Otherwise, thank you very much, Martin, for this talk. Welcome back next week, everybody. We'll have a talk by Devis Tuya, who's a professor at EPFL in Switzerland. And he's an expert in machine learning for remote sensing. And the topic will be machine learning supporting ecology, supporting machine learning. So welcome back next week. And thank you very much, Martin.
Thank you very much for the invitation. See you next week.
See you.
Thank you. Bye-bye.
Bye.
Thanks. Bye.